have one last section to go over, and that is optimization. So optimization kind of has a word problem feel to it. So in that sense, it's kind of similar to related rates. That's the last time we kind of saw we have to read a problem. We have to kind of decipher what information is given and move on from there. So there's that similarity. There's also a similarity in the sense that the calculus is going to be the easy part because we're just dealing with power rule here. The hard part is trying to figure out how all the pieces fit up to that point. Right. So do you remember how with related rates we did similar triangles with cones and all that algebraic step is required to get R, because we had too many variables, we had to either solve for R or solve for H using our proportions. And then after we make that substitution, we still have to clean all that up so that before we can find the derivative. So in that sense, it's similar. The process that we're going to go through is that we're going to have a primary equation, but the equation is going to have too many variables. We're going to need a supporting equation to make a substitution. And then once we get that cleaned up, then it's just derivative and then solving for the missing information. Right. But related rates is time-based, right? Here, time is not going to be independent variable. What we're trying to do is here with optimization, we're trying to maximize or optimize a solution, right? Trying to find, what is the minimum cost for, given these dimensions, or what is the maximum volume given these constraints. Okay, so there's a little bit of also a little bit of a kind of real world application in these types of problems. So let me read through the intro here. Optimization is the process of finding the greatest, which is maximum optimal solution, or least value of a function, the minimal optimal solution, for some constraint, which must be true regardless of the solution. So optimization finds the most suitable value for a function within a given domain. Okay. So the steps that we take is we want to write an equation for the variable that we want to optimize. So basically, we want to identify our primary equation. There are a couple of keywords that we want to look for. So kind of like related rates, we have to kind of use context clues to decide how we are going to begin the problem. So you want to look for words like maximize or minimize, optimal, least cost, greatest size. Okay. We just want to look for one of these words and see what variable or which equation that is describing, and whatever those words are describing, then that is the primary equation that we're going to be eventually kind of focused in on. So after we identify the equation that we want to focus on, we're going to realize that many times the equation is not going to be ready for the derivative step because there's just too many variables in the way. So we need some help. So we need a help equation to get that primary equation, and we want to get that equation down to one variable. Okay. And once it's down to one variable, we can do a little bit of cleanup. From the cleanup, we can find the derivative, and we should only have to use power rule here. We're always going to set the derivative equal to 0, so kind of like finding a critical point, and then solve. And then once we solve for x, a lot of times we're solving for x, we may have to go back and reread the problem and say, okay, what else is the problem asking for? Is it asking for another dimension? Is it asking for a volume? Is that cost? But everything that we are looking for should be already built from the work that we've done before. We shouldn't have to create any new equations. We should be able to just look at what we have and plug in and solve for whatever other information the problem is asking for. Okay. All right, so let's read number 1, and we'll go through each of the steps. So number 1 says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So first step, we want to identify the equation that we want to optimize. So do you see one of those words? And if you do, what is it describing? Yeah, we see the word maximum is describing volume. So we know that's going to be the focus of our problem. We're going to focus in on our volume equation. So let's put a star next to it just as a reminder. Okay, we may have some other equations, but this is really the one that we're going to be focusing in on. So what's the volume formula of a rectangular box?
Height.
Yeah, length, width, and height. Right. So here, length is x, width is x, height is h. So x times h, which is x squared h. But we look at our equation here, and there's too many variables. So we have to understand that we need some help. We need help. Okay, from a second equation. Okay, to reduce our volume equation down to one variable on the right side. So the help is going to come from, let's see, let's reread the problem here. What other information they give us? They gave us information about surface area. So we're going to create an equation for surface area and see if that can allow for the cleanup that we need on the right side. Okay. So let's talk about surface area. Okay, surface area is defined as adding the area or areas of each of the surfaces. Adding the areas of each of the surfaces. So we have an open box here. Okay. How many surfaces are we working with?
6.
Okay, there are 6 sides, right? 6 sides, but how many surfaces have actually material that we have to worry about? So if you look here, what does it mean, open box?
Oh,
just 5, right? So we have a base and 4 vertical sides, and there's nothing up top, so we don't have to include any material for the top. Okay, so let's add up each of the areas of the surfaces. Let's start with the base. Okay, so what's the area of the base?
X squared.
X squared, okay. Okay, what's the area of one of the vertical sides?
XH.
XH, right? And how many vertical sides do we have?
5.
Vertical sides, 4, right? So XH plus XH plus XH plus XH, right? So plus. Okay, so we're just kind of building our surface area by looking at each of the individual surfaces and totaling them up. So we have 1 base, 4 vertical sides, nothing up top, so just 5 sides. All right, good so far? All right, what do you know about surface area? $108. Okay, so we can start there. All right, so this is our primary equation. This is our health equation. We're going to find a way to get this equation to help this one out, get this down to one variable. So look at how these are set up. There's going to be one variable that's going to be easier to replace than the other. Can you decide which one that could be?
X.
X. Okay, let's see. Let's think about that. If I want to get X to be replaced, that means I want to solve for X squared. If I solve for X squared, I'm still left with 108 minus 4xh, right? So that's not going to be a clean, right? Right, the x's aren't going to go away if I replace X squared. So I think h is going to be the easier path, right? So there's only one h here. So if I solve for h, I'm able to get h isolated by itself. Everything on the other side is in terms of x. So I think that's the easier path that we could go. So I'm going to solve for h here, substitute in, and I should be able to get this just all in terms of x, with the h being replaced. Divide both sides by 4x. And now this piece is going to go in here. Okay, any questions so far? So we have two equations. Our primary equation has too many variables. We're going to use the second equation to resolve that issue. And now we've overcome our first hurdle. We should be able to have an equation purely in terms of one variable on the right side. Okay, so we're going along the right path here, down to one variable. Okay, questions there? Now, ultimately, we want to be able to get to the point where we find the derivative and set equal to 0. But this is a little messy for our derivative step. I mean, we could, but then we got to go through product rule. We got to do product, chain, quotient. It's just too messy, right? And this is manageable enough where we can clean this up, and the only thing that we need is power rule. So let's distribute, combine, and what can we do to resolve the bracket? What can we do to resolve the fractions? So now we have to dig into some algebraic steps to clean up. So I'm going to distribute the x squared through. There's only one term in the denominator, so what if I split them up into individual fractions and see if I can clean up each of my individual fractions? And that should help me separate some of these terms. Keep cleaning up. 108 divided by 4 reduces to be 27. One of the x's can go away. One of the x's can go away here, right? I can make this x cubed. And this 4 is in the denominator, so I can push it out in front as what? 1/4. All right, so this is where we want to be, because look at where we started, look at where we ended. It's a lot easier to find the derivative here than it was here, even though these are the same things. Right? So we're kind of working our way down to a relatively easy derivative problem. Right? Okay, any questions so far? Okay, so this isn't like related rates in the sense that there's no time. We don't do dv dt, we don't do dx dt. We're just finding the derivative and setting it equal to 0. Okay, so we're just going to make it v prime And then should be a nice, easy power rule for these two terms. So 27x becomes
27.
okay. Next term. And we're always setting the derivative equal to 0. I'll talk a little bit about why that's the case, but right now let's just go through our steps. So now we just solve for x. Basically, just like finding a critical point. Divide by 3/4, the same thing as multiplying by the reciprocal, so 27 times 4/3. Multiply 9 times 4, which is 36. Take the square root. Plus or minus is going to be involved. However, we're talking about dimension here, right? So negative is not going to make sense. So we're only going to keep the 6, positive 6. Okay, questions so far? Okay, we go back, we read the problem. We have kind of a solution in front of us, but let's make sure we have everything that this problem is asking for. What dimensions will produce a box of maximum volume? So dimensions, we have length, we have width, but what's height? How can we find height?
With the,
Yeah, we have a nice formula, right? We have a nice formula for height, so we just use it. Okay, so just keep in mind that after you solve for x, and if you're trying to find out more information, everything should be available for you. We shouldn't have to create anything else. It's just a matter of plugging in. If it's asking for volume, plug into the volume equation. If it's asking for height, dimensions, plug into the height equation. So we shouldn't have to create anything at the end. It's just a matter of plugging in. So height, 108 minus 6 squared over 4 times 6. That's going to reduce all the way to 3. So we have our dimensions, right? Length, width, and height. So 6 inches by 6 inches by 3 inches. So those dimensions will create the maximum volume given that we only have 108 square inches of material to work with. Okay, any questions?
I don't, like, it's not really a question, like, but when it says maximum volume, wouldn't it, like, why does that matter when it just would be the dimensions every time? Like, does that make sense?
Right, it's like, why, let's see, maximum volume. So we may have different, there are different dimensions of this box that can also create surface area of 108 square inches. So you may have different shaped boxes. They all use the same amount of material, but we want the box that is going to hold the most stuff in it. So it's possible that you may have a really long box, right, that's using 108 square inches, but volume-wise, it's not going to be as great as a 6 by 6 by 3. So you have all these different size boxes that all use the same material, but we want a particular one that is going to hold the most amount of material inside. Yeah. Okay, I'm going to recap the steps. because even though there's going to be some varieties from problem to problem, the basic idea is the same. So I want to kind of recap, make sure that we can kind of see all the different pieces kind of linked together. And then I want to talk about conceptual wise, why do we set the derivative equal to 0? What's the significance of that? And why does that produce the optimal solution? Okay. So first thing is we read the problem and we have to just locate that keyword. What is that keyword describing? It could be cost, it could be area, it could be perimeter. Okay, but in this case it's volume. So from there, you create your volume equation. You look at the right side, you identify the fact that you need some help, right? Too many variables on the right side. So we look at the problem, what other information is given. They give us surface area. So we have our surface area, we build the surface area equation. So the second equation is going to help us get this down to one variable. So we identify H is the easier one to replace. So we replace H in terms of X. Once we do that, we're on the right path. We have our equation in terms of X. And then this is a matter of cleanup, right? We know we're working towards the step where we want to find a derivative, but this is too soon. So distribute, clean up, all the way to the point where we realize that the only rule we have to use is power rule. Okay. So if you're looking at a problem for optimization and you're saying to yourself, okay, I got to do product or chain, you probably didn't go far enough. Okay, so keep cleaning up if you have some parentheses or fractions along the way. So we got to the point where this is a nice, easy power rule problem for both terms. We find the derivative. We always set the derivative equal to 0. We find that critical value, and that's going to be our answer. But then go back, reread the problem. What else are they asking for? Are they asking for volume? Are they asking for another dimension? Are they asking for height? And then every equation that we need is already here. If they're asking for height, you plug in here. If they're asking for volume, you plug into here. We shouldn't have to create anything else once you solve for X. You're just deciding what other pieces we need to find. We're going to see some variations, but generally that's the, with some exceptions, that's generally how we're going to proceed through most of these problems. All right, I want to talk about the fact that, why do we go through this process? Why do we set our derivative equal to 0? And why does that give us maximum or optimal solution? So we have our volume equation in terms of X, right? So this is, we kind of incorporated the height into our volume equation. So imagine we didn't know anything about derivative and we're just going to brute force it and just trying to figure out, okay, what X value will give me the maximum volume? So you test 1. It gives you 26.75. Then you plug in 2. Then you're just creating, let's say you're creating a whole table of values, right? So what X value will give me the maximum volume? So imagine us going through that process and we're creating a chart out of it. So for certain X value, we're going to get some volume, right? If I plug 1 in, I'm going to get 26.75. If I plug 2 in, it's going to give me a higher value, so I'm going to mark it. I keep on plugging values in. I keep increasing the value of X, 3, 4, 5, 6. But then there's going to come to a point where if I keep increasing the value of X, this is going to get larger and larger. Whoops, this will get larger and larger. My overall volume is going to start decreasing. So we begin to see the shape taking place. Right. So rather than testing every value, why don't we just take the equation, find the derivative, and locate where the slope is 0? Wherever the slope is 0, it's going to be whatever solution we're looking for, either the maximum or the minimum. In this case, it's the maximum. So wherever the slope is 0, is going to be where our optimal solution is going to live. So we can skip a lot of unnecessary steps. If we know the equation or the formula, we can find the derivative, locate slope 0, and that's going to be our optimal solution. Sometimes you're looking for minimal cost. So if that's the case, then you're going to be seeking out slope 0 here. But what I want to say is that we don't have to worry about, wait, do I need to do a different process for maximum versus minimum? It's the same process. You just look for slope 0, and that's going to be your answer, okay, for all these problems. So that's why we're always setting the derivative equal to 0. We're looking for these locations of optimal solution. Okay, all right, let's go to number 2, if there's no other questions. Now, your diagram is going to be different from mine, but it's the same problem. Okay. So let me read the problem. It says a rancher has 200 feet of fencing with which to enclose 2 adjacent rectangular regions. What dimension should be used so that the enclosed area will be a maximum? All right. So first things first, what equation are we trying to optimize?
The area.
Because maximum, right? We see the word maximum is describing area. So that's going to be, we're going to zero in on that. That's going to be our focus. I'll put a star next to it. And we look at our shape, and we're going to build our area equation. What's the area of that rectangle that you see in front of you?
X squared y.
Close. Right? Length times width.
2x.
Yeah, 2x, right. Yeah, so x plus x. But that's a common thing to do, that we multiply, but we got to make sure we add. So x plus x is 2x, so length is 2x, width is y, 2xy. Okay. We take a look at our area equation, we need some help, right? Too many variables, we need help from a second equation. And that second equation is the fact that so that is the amount of fence that's perimeter related, right? So we're going to create a perimeter equation as a support that we need for this area equation. So perimeter is adding up all the sides. What's the perimeter of our?
200.
Okay, 200 feet. What about the dimensions that we see here, though?
4x, 4y, 4x.
Yeah. And now we can go back and see, okay, all right, we have 200 feet of fencing, so we'll replace P with 200. We need support that we need to get this down to one variable, right? So we have a couple of options, right? Do we want to, is it easier to solve for x? Is it easier to solve for y?
I think it should be around the same.
About the same.
Yeah.
Okay. So in the instance where it's about the same, you guys can decide. It doesn't matter which one you solve for. But for me, if I realize that they're about the same, I'm going to target x's. I'm going to try to get my equation in terms of x. It's just, you know, we're just used to seeing x's when we're solving an equation, working with problems. So that's just my tendency. But you can solve in terms of x or replace x, that's fine as well. But yeah. Now, not every problem is going to have that equal difficulty, right? The previous problem, we saw that there's obviously one that is easier than the other. So, but yeah, in the cases where you have equivalent difficulty, then you can choose. Okay, so I'm going to solve for y because I want the y's to go away. So this is now going to replace y. So I'm moving along the right path, right? I want my y, my right side to be in terms of one variable. So that's my initial goal. Okay. We want to find the derivative, but too soon, right? This is too soon. So let's distribute the 2x through. Let's separate the fractions. Let's clean up. We should be able to get it down to easy power rule terms for derivative. Okay. Continue cleanup. I like my fractions in front of the variable, so I don't have to look at anything below my variable here. And now everything is consistent, right? It just looks like an easy power rule problem. So look at, yes.
Why don't you distribute the 2x to the 3?
To the denominator?
Oh, never mind.
Yeah. Oh, so you can think of this. You can think of it as 2x over 1. That way, remind yourself that the numerator is only going to see the 2x, the denominator will just see the 1. Okay. So look at where we were. Look at where we got to, and you see that there's a big distinction, right? These are the same things, but we would much rather find the derivative here than here. Right. All right, so now we can find the derivative, a prime. Okay, what's the derivative of my first term here?
0.
There's the x here.
Or 400.
Yeah, 400 over 3. Yeah. Now, if it was just 400 over 3 without the x, it would be 0. Minus, yeah, 16 over 3 x. We have our slope formula. We want to figure out where the slope is 0. So we always set our derivative equal to 0, and we solve for x. Dividing by 16/3, the same thing as multiplying by 3/16. The threes cancel out. My fractions reduce. We go back, we reread the problem. It's asking for dimensions, so we want to find y as well. So we see that we already have a nice y equation that we can use. Plug 25 in for x. So I think that's everything that we need, right? Dimensions. Okay, same process, right? Identify the equation that you want to find a derivative for, If there's too many variables, seek out a second equation to give it that support. Once it's down to one variable, clean up, power rule, derivative, set equal to 0, solve for x. Okay. Yeah, question?
Where did you get 100 over 3?
Right, so the 25 goes in for x,
Oh, okay.
and then I just clean that up. 200 minus 100.
Mr. Yang,
Yes.
why is the perimeter equation 3y instead of 2y?
The reason why is because they specified that there's going to be fence that's going to separate the two regions. So we need to include this middle as well. So the amount of fencing is going to be along the outside, but then also this middle as well.
Okay, thank you.
All right, questions? We'll do one more. This is on the worksheet 1, number 1. This is also area and perimeter, but we have an added element of cost. So let me read the problem, and then we can kind of create the diagram. I'll do the initial setup, but then I'm going to have you guys try to finish the problem on your own to see if you guys are able to work through. So we have so this is going to be area versus perimeter, but something a little bit different here. There's area, but then the cost is going to be very much related to perimeter. So we're going to still think there's a perimeter, but yeah, just have to involve the cost as well as we build our perimeter equation. All right, so we have a rectangular field fenced off along the bank of a river. So I'm going to just create my picture here. Let's say I have a river. And then along the bank of the river, I'm creating my rectangular fence. Only along 3 sides. No fence required along the river. The material for the fence costs $8 per running foot for the 2 ends, $12 for the side parallel to the river. Find the dimensions of the field of the largest possible area that can be enclosed with $3,600 worth of fence. All right, so what are we trying to optimize?
Area.
Yeah, largest possible area. So there we go, right? There's our contextual clue here, context clue there. So let's build our equation for area. I'm going to introduce variables into my rectangle here. I'm going to, whenever I see horizontal, just for me, I like to call it X. Vertical, I like to call Y. But you can choose however way you want to do it. You can choose different variables if you like. Okay, it's really up to you. All right, so what's our area of the fence? All right, we need some help, right? Too many variables on the right side. So cost is going to be the equation that's going to help us out. Now cost, we're going to be adding up the sides, but then there's dollar amounts associated with each of the sides. So we're going to include them. So it says the 2 sides are going to be a little cheaper. It's going to be $8 per foot. The one that is parallel to the river is $12. So we're going to be adding up the products of those information there. So what do you think our cost equation is going to be?
Cost is equal to 8y plus 12x.
Close. We're going to add up all these together. So we have 8y, 8y, and 12x. So what does that combine to be if we were adding all those together?
16.
Yeah. There we go. Right, depending on how long these sides are, we multiply it by the cost, and $16 for the Y length, $12 for the X length, and this result is going to be however much it's going to cost. But you can see the perimeter, right? We're still adding up the size, but there's just going to have, there's an extra element that we have to involve with the cost, with the dollar amount. All right, what do you know about cost? Good. That's what we know how much money we're working with. So using that constraint, we're going to figure out what is the largest area that we can create. So there's our help equation. Does it matter which variable that we solve for or replace?
No.
Yeah, not this time, right? So similar to the previous problem, but again, I'm going to target the y's. All right, so from here, it should feel very similar to the previous problem. All right. Solve for y, get it in terms of x, make that substitution. Once it's down to one variable, clean up until you get to a nice power rule problem. Then you find the derivative, then set the derivative equal to 0, then solve for x. Okay. All right, so try that. I'm going to see how you guys do with this. Your steps should look very similar to what we just did with number 2 on notes. So look at what we did with 2 and see if those steps will help remind you what to do next. Yeah, you do that. Just have to put that in the text so that you want to do one. For those of you who are solving for y, that's fine. It's just that your work may look a little different from mine, but our answer should match at the very end still. Yeah, walking around looks like your steps look pretty good. Just understand that your steps may look a little different from mine if you decide that you want to solve for x. So after we decide that we have our support equation, I'm going to decide to solve for y. So I got 3600 minus 12x over 16, so that replaces the y. Now I'm down to one variable. Clean up. Separate. Yes.
Why did the 12 over 16 turn into 3 over 2?
Oh, that's the derivative. So So here, that is where we want to be. I think that's what you got, right?
Yeah.
And then you find the derivative, and it becomes 6/4, and that should reduce to 3/2. Okay, so understand that once you make your substitution, derivative should not be the first thing in your mind. You should be like, all right, I want to clean this up so that my derivative is easy. You want the derivative to be easy. So you're going to spend the time to clean up. Once it gets down to this, now you're ready for the derivative, right? 225x becomes 225. 3/4 x squared becomes 6 over 4x, which reduces to be 3/2. Once you have our derivative, we always set it equal to 0. Solve for x. Divide by 3/2, the same thing as multiplying by the reciprocal, by 2/3. So I got x equals 150. But if you decide to solve for y first, you should have gotten 112.5 first, and then you can substitute in to solve for x. All right, any questions? So there's a couple more scenarios that I want to do. We'll save it for tomorrow. Those scenarios are where we don't need a supporting equation, but the idea is the same. We still want to get that equation cleaned up so that the derivative is nice and easy, so that we can find our critical point just by relying on power rule. Yes.
On Thursday, or so this isn't related to this, but it's on Thursday. We have class with the PSAT.
So tomorrow we'll have class. Okay, so tomorrow we'll finish optimization. We'll do a little bit of review. We'll start review. I want to do a little bit of work with derivative graphs, right? But Thursday is PSAT day. So no class. No class, no homework. It's only a half day for students who are here. Friday we will do review. Monday, we'll do a little bit of review. We'll do 5.1. We'll start the next section, which is not on the test. Tuesday, selection day. Wednesday, review. Next Thursday will be your test. I hope to finish grading your quizzes today so that I can give it back to you tomorrow. Okay. And if you're not here tomorrow, I hope to have it in the grade book so you can see what you got. Okay, if you're on Teams, have a great day. See you guys tomorrow.
Thank you, Mr. Yang.
Thank you. See you guys.
They did all of our